we go. Imagine with me that you are sitting at a stoplight. The quality of the vehicles you've driven in might matter, they might not. But all of a sudden, the driver slams on the gas. What do you feel? What is that experience like to you? Sorry? You feel like you're getting pushed back. Why do you feel like what do you mean you're getting pushed back? Like you're getting slammed into your chair? Is that what you mean? Say that again. There's a force pushing on your... You said one thing and then you gestured to your chest. It feels like there's a force pushing on your chest into you as the car accelerates forward. Go back into the seat. Okay. It feels like you're being pressed back into the seat. What else? How else would you explain that sensation? The sensation of being, well, of the car accelerating around you. Because you know you're going forward, right? Like the car is moving forward, you are moving with the car. So being pressed back into the seat it might be what you've experienced. I'm not going to devalue that at all. But it kind of seems counterintuitive, doesn't it? If you think about what's happening here. The car is moving forward, so are you. And yet you feel like you're getting pushed backwards. So if you had to make an argument for what's actually out, because clearly you're not getting pushed backwards. Otherwise, the car would like fly past you as you stayed still, right? Which would be awful for you and the car. You end up going forward, so something has to be pushing you forward. So why does it feel like you're getting pressed into your seat?
Because the car is moving faster than you are.
Because the car is moving faster than you are. And what do you mean? Elaborate on that.
Because you're not attached to everything when the car is moving forward. Because you're not attached, you're not accelerating as fast as the vehicle.
So you don't accelerate at the same rate.
No.
Your body wants to
stay where it is.
What is that tendency called? Do you know?
It was one of Newton's laws.
It was one of Newton's laws. Yeah. Yeah. It feels like the thing's flying back, but is the thing flying back? Because that wouldn't make sense, right? If you toss your phone on the dashboard and then you accelerate forward, what you experience is the object flying to the back of the car. But is that what's happening? So what's happening then here today? Yeah, in three-dimensional space. Like if you're an observer from outside the car and you're watching all that happen, the thing on the dash stays on the dash while the rest of the car moves away from it. Your perspective is skewed because you are inside the object that's accelerating. So that our perspective and what we assume to be true about what's happening, as soon as we start to think a little bit critically about it, I'm hoping you can see that that's not actually what's occurring. The phone isn't getting flung to the back of the car. It's staying still, and the back of the car is getting flung towards it. The effect is the same. Whoever's in the back of the car is getting a phone to the face. But the mechanics for how that happens is slightly different. There's a name for this. It starts with an I. Yeah, it's inertia. So it's an important concept to talk about at this point. Inertia. Inertia is why you feel like you're getting pressed back into your seat, but you're not getting, because nothing's holding you down, right? It's not like someone all of a sudden is sitting on your chest, even though that's sometimes what it feels like. So what's actually happening there? That pressed back into your seat is actually, yeah, the seat enveloping you. I'll say it this way, the seat pushes up to you. And this is the concept of inertia. I mean, Vine described it right, you're not attached to the car as rigidly as some of the other things are attached to the car, and so when it moves forward, there is a moment in time where you're not moving forward yet, and it feels like you're getting sucked back into the car. And it depends on the kind of car you do this in. My first car was a 92 Civic. If that's the car we're testing, you're not going to feel anything because you're probably going to accelerate at the same rate because my 92 Civic is a 92 Civic. But when Teslas first came out, I had a buddy who had decided to invest early in Tesla, and he managed to buy himself a Tesla right on. And he took us all for a ride. And it was late at night, and we would sit on the road, and he's like, watch this. And he slams on the gas, and the car goes, or not gas, slams on the accelerator, and the car goes immediately. There was no hesitation. And we just got sucked in, right? Is what it felt like to us. But really what's happening is the rigidness of the car, the seat accelerates with it, and whatever cushioning is there gets pushed up into you and envelops you. The concept of inertia is what's at play here. Inertia is the tendency for an object to maintain its motion. Is that all on the screen? It is on the screen. So if you're not moving, your body wants to not move. If you are moving, your body wants to keep the motion it has. And so a lot of what we experience as acceleration, especially in a car, can be attributed to this idea of inertia. So it feels like you're getting pushed back into the seat, and that's because your body's tendency, and especially as you get bigger and bigger and bigger as a human being, like my daughter at 40 pounds versus me at 220, is going to experience this fundamentally differently. I have more mass than she does. I have a greater amount of inertia than she does. I'm going to be harder to get moving, and equally as important, I would be much harder to stop, for example, if I was running at you. Or in the car. The car all of a sudden now comes to a stop. You're driving at 50 kilometers per hour when the driver slams on the brakes. You feel what? What is your experience in that motion? Yeah, it feels like you're getting launched forward. But if you think about it now in this context, what is actually happening? You're not getting launched forward. The car is slowing down faster than you are. The car is not going backwards yet. That would suck if all of a sudden the car was going backwards. That would tear you in half because of the lovely thing we call a seatbelt. If all of a sudden the car went from 50 forward to 50 backwards in an instant, it would separate you from parts of you. But it is, as Liam said, it's not moving it forward as fast as you were. And so you continue at the speed you were at, and the rest of the car starts to slow down behind you. So the seat is going to, the frame is going to slow down first. With the seat, your seatbelt's going to have a little bit of give, but if you're wearing it, it's going to hold you back. If you're not wearing it, what's the next line of defense for you? What's going to stop you if you're not wearing your seatbelt in a car that is now coming to a very sudden stop?
I don't know if the windshield is strong enough.
It's going to try. The windshield and the dash are going to work together to try and contain you. The dash is probably going to hit you in the thighs as the windshield hits you in your head and shoulders. Depending on how fast you were moving, the windshield will be strong enough to slow you down, but might not be strong enough. The terrifying thing is it might not be strong enough to stop you entirely. You may. I mean, the opposite is also true. The windshield doesn't do a great job of, I mean, it actually does a better job of things coming at you. If you've ever seen a car accident with a deer, I've seen car accidents with deer, and the deer is halfway through the windshield. So it is strong enough to do stopping. It's awful. It's disgusting, but it's a thing. So launched forward. That's not what's actually happening. I'll write down what Liam said. The car is slowing down quicker than you are. The car has more inertia. So as it slows down, it slows down more aggressively than you do. The same thing with it's the opposite of the phone on the dash. That's why when we toss things in the back of the car and slam on the brake, all of a sudden that thing is no longer in the back, it's now in the front. It was moving, it wants to continue to move. Now here it is. So what is actually happening is actually the opposite of what we were experiencing. And in a car, a seatbelt holds you back, which we know. So the things that you're feeling are feelings of acceleration, even if what you're interpreting, even if your interpretation of those feelings is incorrect, those feelings are acceleration. We often have another word for acceleration that we're not going to use a lot. Typically, when we think of something accelerating, we think of something speeding us up forward. When we use that word acceleration, that's typically what we mean. We are going to use it in a much more broad sense. But at this stage, what would you call something where you're slowing down but still moving forward? We have a word for that too. Deceleration. Things get weird, or there is weirdness, when v, your velocity, and a, your acceleration, are in opposite directions. How we interpret those things gets weird. As long as you maintain some of the stuff that we're going to establish, I'm going to establish some norms that we're going to use to talk about physics within those norms. As long as you can stay there, you'll be fine. But things get weird when we talk about, like, I'm accelerating backwards while I move forwards, or I'm accelerating forwards while I'm still moving backwards. Like, how we interpret that is going to get a little bit weird. So acceleration is the push that you feel when your velocity changes. This is an important piece of this, because velocity is what kind of mathematical object? We have two mathematical objects that we're dealing with in physics: scalars and vectors. Velocity is a, yes, Vian, say it louder. I think it was you who just said it, or was it Liam? Oh, I thought you said it. Velocity is a vector. Because velocity is a vector, velocity has a magnitude, and it has a direction. And when you accelerate, if we're talking about an acceleration being a change in your velocity, either of these can change. And they can change independent of each other. For example, I could do this, right? I'm walking, I'm just something over here. I'm walking, I'm going this way, I can do this, and I can do this. There was a change in the magnitude of my velocity, even though my direction was the same the whole way. Okay? Or I can do this. Here, I can actually move over one seat for a second. And I want to put your hands straight up. Yeah, like that. Higher. Yeah, thank you, right there. Okay, or I can do this. Hang on. Did the magnitude of my velocity change at all? No. Like, I maintained the pace I was at, right? But what happened? I was walking forward. Again. And what are you feeling? Well, you're feeling kind of pulling me this way, yeah? And I'm feeling you pull in on me. So my magnitude stayed the same, but all of a sudden my directions changed. If I was doing it faster, or in a car, for example, how do you experience a turn like that in a car? Kind of, yeah. If I'm sitting in the back of a car, I mean, the driver's experience is always different because your body braces for things in ways that your passenger never could. So a driver, if you are the driver, try and get your head out of that and think about it as a passenger. You're in the back seat of a car. Maybe you have the misfortune of being shoved in there with a bunch of you all making a lunch run, and there's 4 of you in the back seat. You're legal. There's 4 of you in the back seat. You're all crammed in, and you're just giving her. Got to get to McDonald's and back before lunch ends. and your driver makes that turn, what happens to the person on the outside of that turn? You get squeezed into the car, right? The car is making the turn around you, and if we tie it back to this idea of inertia, your body wants to keep going this way. But what happens? The car says, no, we're going this way. So if I grab your arm and I make the corner, I'm not going to do it yet, but thank you. If I grabbed your arm to make the corner, I'm getting pulled in this way. Or if it's the car around me, there has to be a push into the corner. There's a push into the corner to make that change. Either way, the way we experience this, the change in direction isn't always necessarily super intuitive until we stop and think about the entire picture of what's going on. So if I want to be going that way, something has to push me in to make that change. And because velocity has those pieces, acceleration can change either one of those things, sometimes both, but not always, and still be considered an acceleration. You with me, Akash? Okay. So the formal definition for acceleration is the rate of change of velocity. So because acceleration is dependent on velocity, because velocity is a vector, acceleration must be as well. So it's also a vector. We use the symbol A, and if it's dependent on the change of velocity, we're going to use that symbol delta that we used for change in before, and velocity had that symbol V with an arrow above it. So acceleration is not just the change of velocity, but how quickly it changes. So it's not just the rate of change of velocity, but it's the rate of change of velocity with respect to time, as time is passing while you're doing this. So this can also be written, because we have a change in velocity here, this can also be written as we would write a change in something. That delta V can be rewritten how? Who remembers? Yeah. Sorry? Louder. I can hear you. How can I rewrite delta V without using the delta? Like, what is a mathematical equivalent statement to delta V? Yes. V final minus V initial during some time. So this thing has units as well. If we look at the units for velocity, the units for velocity are in SI units, typically meters per second. And time is measured in seconds. So sometimes it's quoted as, excuse me, a meter per second per second. Sometimes you'll see it written like this, a meter per second per second. But equivalently, I can write it slightly differently. When I'm dividing a fraction by a whole number, this is the same thing as multiplying that fraction by a fraction with that whole number in the denominator. This is what I'm doing with my math nines right now, blowing their minds. And if I just take a look at what I've got here, a meter times 1, that's just still going to be a meter, and then seconds times seconds, that's seconds squared. So the units that, especially in North America, this is much more European way to write it, a meter per second per second. This is a much more North American conventional way to write it. It's also an SI way to write it. The meter per second squared, or how fast is my velocity changing? My meters per second are changing every second. So there's two ways to interpret this meaning. And honestly, I think this way of thinking about it is the green way, where I wrote it above, is actually easier as far as helping our understanding. This is a lot cleaner, a meter per second squared. But as far as helping our understanding, this green way is an easier way to do it. Because what does it mean for an object to accelerate at 2 meters per second squared? If that's the acceleration, what's happening? And again, I'm going to force in that positive there at positive 2 meters per second squared. Yeah. Yeah. So, yeah, you're gaining, which, and I'm going to fill in that chart here in a second, exactly the way you described it. We're gaining 2 meters per second on our velocity every second. So we are moving faster as time increases. So at t equals 0, let's assume that at 0 our velocity is 0. At 1 second, we're now moving 2 meters per second if our acceleration is 2 meters per second squared. After 2 seconds, we've gained another 2 meters per second of velocity. Now we're moving at 4 meters per second. At the 3 second mark, we've gained another second and therefore have gained another 2 meters per second on our velocity. Now we're at 6 meters per second. So our velocity is increasing with this constant acceleration. Now sometimes students are like, yeah, okay, meters per second squared, but we talk about our velocity being in kilometers per hour. So what about kilometers and hours as the units we use for acceleration? I'm going to show you why we don't do that. Why meters per second, even though thinking about, like, it doesn't really connect with our experience, right? Like oftentimes we're sitting in a car and we're accelerating over as we leave a stoplight up to speed limit. What is the acceleration typically in a car? What do those numbers look like? 2 meters per second squared. This seems like a fairly small acceleration. 2 seems like a fairly small number. Let's look at what that acceleration is in a different set of units. 2 meters per second squared. I'm going to convert this thing into kilometers per hour squared. That would be the equivalent acceleration. So I'm going to multiply this first. I want to put kilometers on the top. I want to multiply some meters on the bottom. So 1 kilometer is 1,000 meters. So that gets rid of my meters in the numerator. I'm going to put my kilometers up there. And now I need to turn seconds squared into hours squared. For the sake of space, does anyone remember how many seconds there are in an hour? 3,600. So I want to put hours in the denominator, so I want to put seconds in the numerator. There are 3,600 seconds in 1 hour. And doing this once gets rid of one of my seconds, but I don't have 1 second, I have 2 seconds. I have seconds times seconds in the denominator. So I have to do that again. I hope we can see here that this number is going to get very large very quickly. We're multiplying it by 3,600. We're multiplying that by 3,600. And yeah, we're going to divide by 1,000, but we've already multiplied it by 900,000. The number we're looking for here is 25,920 kilometers per hour squared. A 2 meter per second acceleration extended over an hour, you're going to be moving pretty quick. That's equivalent to gaining 25,920 kilometers per hour worth of speed every hour. And the only place you're going to experience that kind of acceleration is where? I'll give you a hint. You're probably never going to get there. Space. The odds of any of us getting to space are, unless you have aspirations to be an astronaut, then all the power to you. Statistically, it's not super likely for me to become an astronaut. Okay? So this 2 meter per second squared is the same as saying I was accelerating at 25,920 kilometers per hour squared. Both of these numbers are ridiculous as far as connecting with our everyday understanding of acceleration. You're going to be driving a car at 50, 60, 70, 80, 120 maybe kilometers per hour, and your accelerations are all going to be within that window. Talking about an acceleration like this is as ridiculous as talking about acceleration like this. We just have to get more and more comfortable talking about velocities this way so that we can accept what these accelerations look like. Flip the page. Let's talk about those directions, shall we? The rules for direction are the same for acceleration as they are for velocity and displacement. So typically speaking, we assume that forwards, up, to the right, generally speaking, we all consider those to be positive directions. And so as long as, what I'm going to do here is I'm going to write like this. We're going to call that way for all of these number lines. That way is going to be the way that we consider positive. Now, what I'm going to try and convince you of and rework your thinking here is that a negative acceleration does not mean that you are necessarily slowing down. Negatives are just the direction you're accelerating. Whether you're slowing down or speeding up depends on which way you were moving to start. Here's what I mean. So let's say I've got an object here with a velocity this way. So I've got an object moving to the right, and my acceleration then is also that way. The way I've labeled it, these are both positive. My velocity is positive, my acceleration is positive. So if I look at just this, what does a positive velocity tell you in this context? The object is doing what? Just forget the acceleration. Just look at the velocity part. V being positive here tells us the object is moving which way? I made to the right positive. So if this number is positive, the object has to be moving right. This symbol is just connected to the direction of travel. Now, if I'm also accelerating in the same way that I'm already moving, what's that going to do? I was moving forward. I am being pushed forward. So what's going to happen to my motion? It's really easy. Someone say it. If I'm getting pushed in the direction that I'm traveling, do I have to push someone in the direction that they were already traveling in? Should we do this? Just hear it. Humor me. Class is too quiet today. Actually, no, what? No, just hear it. You'd be hitting a desk if I did this. Fine, second. Or, I want you to pull your chair into your desk. I want you to get in the chair. Okay. Let's call that direction positive. Bring your feet up. Thank you. Yeah, that works too. That's safer, probably. Brace your face. That's good. He's moving forwards, and I give him a push. What happened to the speed that Brian was experiencing? Moving that way. I pushed him that way. What happened to his velocity? It went up. More positive. He sped up, right? If your velocity and your acceleration are in the same direction, you're going to speed up. Okay. Let's just do them all while we're here. Write in the notes. We have time. There's only 5 minutes left. Okay, so my next one. What happens if the velocity, so here we go. The velocity is forward. So this velocity is forward. And now I pull him backwards. What happens? What happens? He still moved forward, yeah? Let's do it again. Do it again. The velocity is still positive, but it started to decline, right? So with a positive velocity and a negative acceleration, he was still moving forward, but he slowed down. Thankfully, because otherwise he would go on. Likewise, you know what? Likewise, if he's moving backwards, this is negative, and I all of a sudden accelerate him forwards. I'm moving fast. Okay, here we go. Mine's moving backwards. And he accelerated which way? Again. I'm just going to let go. He's moving backwards. Velocity is negative. And something brought him to a stop. For something to bring him to a stop, which way would he have to be accelerating? velocity was negative. The negative velocity started, when a negative starts to decline, it moves towards 0, right? As a negative number starts to decline, it gets towards 0. And so if he's moving this way and slows down to a stop, his acceleration had to be which way? Yeah, right towards 0, or forwards the way you're facing, right? The only way you come to a stop, moving backwards, is if something pushes you from behind. In this case, the bearings, the friction in the wheels, will slow you down. But if I do that again, what if I do type of move? So I'm doing it, y is moving. Alright, so now he's moving negatively, and I start to accelerate him negatively. Those things are going to combine to speeding him up. So in this case, a negative acceleration actually makes him move faster. It just makes him move faster backwards. So it's that combination of how fast and which way, combined with the direction of our acceleration, that's going to determine what's actually being experienced by our classmate in this case. Thanks, Nancy. What time we got? Oh, we got 4 minutes. We can write that down. Okay, here we go. Let's put it all together. So a positive acceleration and a positive velocity mean you're moving forward, and gaining v. Typically, we call this speeding up. And this is the easy one. If I have an object, there's Vian in the chair, and he is moving forward, his v is positive, but his acceleration is negative. So this is a negative a and a positive v. What that means is he's moving forward, and this was him moving towards the door, moving forward, and losing v. If you're moving forward and losing v, we typically call that slowing down, or we experience that as slowing down. If I've got a negative v and I have a negative a, so a is negative, v is negative, the negative v tells us we're moving backwards. And gaining v. The magnitude of our velocity is getting larger. So this is just speeding up backwards. Speeding up backwards. Which is our least favorite thing to do. It's wildly unintuitive. If you're in a car accelerating backwards, you should feel uncomfortable. It's not something we're used to doing. It's easy to lose control because you're not used to this. If you're playing football, do you want to ever be accelerating backwards playing football? No, unless you're the quarterback taking a couple steps back. Because if you're accelerating backwards, it means someone's running you down. Generally speaking, a negative experience. Have a great weekend. We'll finish this on Monday. I hope to get your tests back to you on Monday as well as these quizzes. We'll see how that happens, though. See you guys later. Sorry? Oh, possibly. Maybe I'll use Alexis next time. Maybe.